2005, in Wiltshire, England, there was a young student who was about to start school at the University of Nottingham. This student's name was Alex 2. Alex didn't have a lot of cash, and so like a lot of students, he was going to take out student loans to pay for his education. But the high costs troubled him, so he sat and brainstormed a few ideas, and something struck him.
It was about midnight, and I was brainstorming away. I just thought, well, I'll sell 1 million pixels for $1 each.
Alex's idea was to build a website with a 1,000 by 1,000 image grid and sell each pixel for $1 each. If he sold the whole image, he'd end up with $1 million.
Well, the $1 million homepage was something that I created because I was broke.
He told all his friends and family and managed to raise about $1,000. Then he used that money to issue a press release to draw even more attention to the site.
The first thing that I did, I told all my friends and family, right? And luckily that press release got picked up by the BBC and some newspapers in the UK. And on the day those articles went out, the site made like $2,000. And then the next day it made like $2,500. And then it made $3,000. And once the ball was rolling, it was like there was no stopping it. It was like the snowball effect.
And in 4.5 months, the page had sold out.
There was one day, it was New Year's Eve. And the site went ballistic, and there was 20,000 people logging on every hour. And the money was just flowing in at a rate of about $100,000 an hour.
But it wasn't all rosy. During the auction of the final pixels, there was an extortion attempt where a group demanded $50,000 or they would take down the site. Alex didn't pay, and they initiated a DDoS, and they brought down the site for a whole week. The attack eventually subsided. Alex sold his final pixels, and the $1 million homepage is still with us today. In this course, we're going to build a version of the $1 million homepage as a decentralized app on the Ethereum blockchain. Alex used PayPal to process his payments, but we're going to accept our payments through Ethereum. Alex's site was brought down by attackers, but our pixels will live on the Ethereum blockchain and no attackers can bring them down. Alex put his pixels up for auction on eBay, but we're going to auction our pixels directly in Ethereum with a smart contract. I want to be clear here. I am not trying to get you to build a copycat site, and I'm not trying to teach you how to get rich. Instead, the Million Ether homepage is a perfect introductory decentralized app because it touches on many of the ideas that we can bring into other DApps. For example, in building this app, we'll talk about how to build a user interface using HTML and JavaScript in the browser that connects to code on the Ethereum blockchain, how to write smart contracts that control their own funds, how to auction scarce digital goods in smart contracts. We'll also talk about patterns for robust Solidity code, how to track real-time events on the Ethereum blockchain and push them to our browser using WebSockets, and security considerations for writing smart contracts so that you don't have your funds stolen. This course is for getting started with Ethereum and Solidity programming. We walk through every step on how to build a Million Ether homepage from empty folder to the blockchain. If you want to learn the practical steps to building a full-stack Ethereum DApp, then this course is for you. Let's get started by looking at how we store pixels on the blockchain.
It's a bit crazy, and the internet is the perfect place for crazy ideas.
To create our page, we're going to be storing pixels in an Ethereum smart contract. To store colors, we have to pick a format to encode them in. Every byte we store on the Ethereum blockchain costs Ether, so it's important that we're careful about what format we use to store our pixels. Thankfully, we don't need to invent our own format. We're going to use 24-bit RGB color. What that means is that we're going to store 1 byte each for the red, green, and blue component of each pixel. For example, when we use the color picker in Chrome, we can specify colors in RGBA. RGBA stands for red, green, blue, alpha. Each one of these is called a channel, as in the red channel or the alpha channel. The alpha specifies the transparency of the color, which we're not going to use, but you could if you wanted to. Notice that as we pick a different color, the values for red, green, and blue vary as a number between 0 and 255. That's because each channel is represented by 1 byte. And I can understand if you haven't been working with bits and bytes recently, so recall that 1 byte is 8 bits. A bit can hold 2 values, either 1 or 0. And with 8 bits, we can hold 2 to the 8th values, which is 256 values. In JavaScript, we can convert numbers between bases like this. This converts 255 in base 10 into binary base 2. There's another common way to view the bytes of a color code, and that is hex encoding. If you've done any web development at all, you've probably seen this. This is just another way of encoding the same thing. Each RGB channel is encoded in 2 base 16 letters, which are then concatenated together in one string. So to convert our RGB value to hex, we could do this. We'll convert each base 10 string to hex. and then we'll concatenate them together. And notice that this is the same hex code we see in our browser for that same color. But there's one caveat here that's specific to our implementation. Conventional hex color codes require that the hex code have exactly 6 digits. But if our input channel is less than 16, we are only given a single digit. Here, we're given a single digit C, and that's incorrect. It should be 0C. We can fix this by a JavaScript trick where we prepend zeros and then slice them off. We can also convert colors the other direction, that is, from hex back to base 10. In this case, we're taking a base 16 number and converting it to base 10. We'll use this sort of conversion throughout the course. We're going to store our pixels in our smart contract storage as 3 raw bytes. When we draw this pixel in our browser's canvas, we're going to convert from these raw bytes into base 10. When we upload pixels to our page from an image, we're going to convert the decimal colors back into hexadecimal. We're not going to do a lot of bit manipulation in this series, but because we're passing pixels around, understanding this color encoding helps a lot. Let's build the essential contract for the million Ether page. First, let's make a place for it. And then I'm going to edit contracts, millionetherpage.sol. We're going to be storing our pixels in a 1000 by 1000 grid. The 0, point is the top left, with X increasing to the right, and Y increasing towards the bottom. Remember that we're storing each pixel as 3 bytes. The data type for this in Solidity is bytes3. In our contract, we'll represent this grid initially as a 2-dimensional array of bytes3. This array is going to be stored in our contract's storage. That is, every node on the Ethereum network will hold a copy of these pixels. We'll mark these pixels public, which means that Solidity will automatically create a public getter function to read these values. To set a pixel color, we'll use the function colorPixel. It accepts an unsigned integer for the X and Y location and a bytes3 for color. When this function is called, it will update the pixel at the appropriate location. Now, this contract is simple. We're storing 1,000,000 pixels in our contract with no restrictions. This is just the first version. Over the next few videos, we're going to talk about how to bid for and buy pixels, how to emit events when pixels change, and how to give refunds when someone is outbid. While these ideas might sound simple, there are a lot of tricky details that we're going to work through along the way. But for now, this contract gives us the foundation to test our DApp end-to-end. As a sanity check, let's deploy this contract to our local network and try reading and writing pixels. We'll compile and deploy this on the command line, and then we'll look at some tools to make it easier in the next video. Let's compile our contract using Sulk.js and generate the ABI. If you watched the earlier course, we created our own private testnet in Geth. I'm going to be using that testnet for this video too. If you don't have a private testnet, go back and watch it. We'll also need a couple of accounts that have mined some Ether locally. Let's start up Geth in the console. You can find this command in the notes. The first thing we need to do is unlock our account. Something you should know is that you can set a time limit for the unlock by using the third parameter. I'm going to unlock my account for 24 hours. If we restart Geth, you'll have to unlock your account again. Now let's copy our contract bin. You can select it to copy and paste, or I'm on a Mac, so I'll use pbcopy. And then flipping back over to the Geth console, we'll type var contract code equals, and then paste the bytecode of our contract. And we submit the transaction to create an instance of the contract on the blockchain. Notice that we have our contract address via the contract key here. Let's save that. And remember that your contract address will be different than mine. Of course, before our contract can actually be used, we need to mine the transaction. We'll do that by typing miner.start, wait for it to finish, and then type miner.stop. We also need our contract's ABI, the interface description of our contract's code. Again, copy this, and flipping back over to Geth, we say var ABI equals json.parse, and then paste it in. Take a look. Next, we create a JavaScript class for our contract. and then we create an instance of that contract at a particular address. Now we can check the value of a particular pixel, let's say pixel 1, 2. And this is 0, just like we'd expect. Let's try changing a pixel by sending a transaction. I'll type mep.colorPixel.sendTransaction, then we put the coordinates 1, 2, and then a hex code for the bytes 3, which will represent the color. Now, this won't mutate our contract state until the transaction has been mined, so let's mine this transaction. And stop the miner. And let's check the value of pixel 1, 2 again. It worked, great. Of course, this contract is a bit silly. Anyone can overwrite any pixel essentially for free. Let's work on making this better. In this video, I want to give you a quick tip on how to only mine blocks when there are transactions. More generally, this will show you how to load utility scripts into your Geth console. Here's the problem. When we're developing smart contracts, every time we want to make a change, we have to issue a transaction, and that transaction has to be picked up by a miner. Eventually, we'll deploy contracts to live test networks or to the production network, but for testing, we just run a local node. Ethereum miners, by default, mine blocks very quickly, regardless of whether there are transactions or not. The mining process can be CPU intensive. The problem for me is that I'm generally developing on my personal laptop, and I don't have a lot of extra CPU to spare. Fortunately, we can use this script, which can be found on the Ethereum wiki, which will start and stop our miners automatically, depending on if there are transactions to be mined. Let's copy and paste this code into a file. Now, you could just copy and paste this directly into your Geth console. That would work. But Geth also has a load script helper function that we can use to load this and any other helper functions we might want. So here I'll type load script and then the path to our script. If you get the path wrong, this will return false. If you have the correct path, you should see no transactions, mining stopped, and it will return true. Now let's try this out. Let's send Ether from one account to another. We'll type eth.sendTransaction and specify a from account, a to account, and a value. Great, it works. Our miner automatically starts and stops, saving our precious CPU. One thing to note is that this script added in listening hooks, and it didn't save a handle to turn them off. If for some reason you don't want this behavior, the easiest way to get rid of it is just restart Geth. I want to give you another tip that will save you tons of time. When developing your smart contracts, use an IDE like Remix. In our videos, we've been compiling our smart contracts by hand using Solk, and this is a good idea for learning what's going on, and it's a best practice for production contracts. That said, when we're in the early development stages, copying and pasting bytecode and ABIs can be a real pain. Thankfully, there are editors like Remix that make this a lot easier. But I want to give a disclaimer first. In this video and in this course, I'm going to be using Remix as a tool to quickly compile, deploy, and experiment with smart contracts. I want you to know that Remix is not essential. You can and should be able to do anything I'm doing in Remix on the command line. We've covered how to do it in earlier videos. Remix is a tool to make our lives easier, but it's not a requirement. Another thing I want you to keep in mind is that Remix is under active development. I'm using the most recent version of Remix, but by the time you're watching this video, the design might have changed a little bit. If you see me using a feature that doesn't appear in the same place in your version, check the comments section for updated instructions. With that in mind, let's take a look at Remix. There's a deployed version of Remix at remix.ethereum.org. You can also find the code at GitHub. In the main pane, you can see some default Solidity code. On the left, we have our file explorer, and on the right, we have some tools. For our development, we need to connect this page in two ways to our local computer. One, we're going to connect the Remix file pane to our local file system using a tool called RemixD. And two, we can connect this page to our local Geth test network using Web3. Keep in mind that we need to be very careful about security here. It's probably fine in this case to connect to your local Geth instance as long as it doesn't hold your real private keys. That said, if you want to be extra careful with your security, I'd recommend downloading Remix from GitHub and running a local instance instead of using this hosted instance. The hack scenario here would be where an attacker hacks the hosted version of Remix and secretly configures it to steal your private keys. This hasn't happened yet that I know of, but better safe than sorry. Let's connect Remix to our local file system using remixd. You can view the GitHub repo for remixd here, which gives you installation instructions. Right now it uses npm install. We use it by starting remixd and passing the path to the directory we want to use for our contracts. Now back in Remix, we can click the chain connect icon above the file browser. And if you're lucky, it will connect to your local remixd. Here you can see that I'm working on the millionetherpage.sol. Remix can run our code in a variety of environments. The default environment is a JavaScript implementation of the EVM. The JavaScript version is really fast, but it all runs within our browser. Instead, what we're going to do is connect to our local Geth node. This will let us use Remix as an interface to our local durable blockchain. We can also perform actions on the Geth console that affect state, and we'll be able to create a web UI that also reads from that same Geth. By connecting to Geth, we can use it as a central access point. In order for this to work, you need to have started Geth with the correct RPC options. Here's one Geth command that would work, though we'll use others in other videos. To connect to our local node, we'll pick from the dropdown Web3 provider. Right now, the default says localhost port 8545. I have to use 127.0.0.1 to connect to my machine. If it worked, you should see your accounts dropdown change. Within this Geth instance, I already have some accounts, and so they appear in the dropdown along with the amount of Ether in each account. If we click the contract details, you can see a number of helpful info panels. For example, we can see the compiled bytecode, the ABI, the gas estimates, and even the assembly. Deploying an instance of our contract is super easy. We can create an instance on our blockchain by hitting Create. This will submit a transaction to our Geth node. And remember, you'll need to mine this and any transaction you send there, so make sure that you have a miner running. After we deployed, you can see that we have an address for this instance. We can copy this address, save it, and use it in the Geth console or in our apps. Notice that Remix also reported the amount of gas required to create this contract. Another thing you might notice is that the methods on our contract object now have form fields. One of the best things about Remix is that now we can use these forms as a minimal UI to test our contracts. Let's test it now. In this contract, we're storing an array of arrays of pixels stored as bytes3. We can get the value of any particular pixel by using the pixels function. If we wanted to get the pixels at, say, 7.4, you can see that it returns 0. To set the color of a pixel, we need 3 arguments: the x index, the y index, and 3 bytes. The x and y index are easy enough, we just pass the numbers themselves. But passing 3 bytes is a little awkward. What we have to do is pass each byte itself as a hex-encoded string. So here we have an array with 3 bytes, each byte individually encoded as hex. After we submit that transaction and it's mined, we're given back a transaction receipt, which we can inspect to find the block number of that transaction as well as the amount of gas used. Notice that the from field is our account address, and the to field is the address of our contract. Our contract's account address lives on the blockchain like any other address. Another thing you can do with Remix is debug particular transactions. I'm not going to walk through it here, but click on the Launch Debugger button to walk through the EVM opcodes that happened during our transaction. Now we can check the value of the pixel 7.4 by using pixels again. Notice that it returned our color in hexadecimal. Nice. Let's say that you refresh the page and you want to get set up again. You'll need to reconnect to remixd and also to your Web3 provider. If you want to reuse an old contract, you can click the @address button and then paste the address of an already deployed contract. This will let you interact with that contract and keep its state. So that's the basics of Remix. It might change a little by the time you watch this, so check out their docs for the latest. And you don't have to use Remix, but we're going to be using Remix a lot in these videos, and it's going to save us a ton of time. Our contract has 1 million pixels. At some point, we're going to want to draw the image that all the pixels create. Our current pixels method lets us retrieve one pixel at a time. That would take 1,000,000 calls. I'm sure we can do better than that. A first try might be to create a function getPixels, which just returns them all. If you try this, it may or may not work. It will be slow either way because it's a good amount of data. Another idea we might try is to just get each row. This will work in a pinch, but it still requires 1,000 calls, one for each row. When we build the UI, we probably want to cache the image so we don't have to keep reading it from the blockchain. If we had a script to periodically recreate the image, making 1,000 local calls isn't that big of a deal. However, it would be great to have a real-time component to this page. We want any visitor to this page to automatically see any new pixels the instant that they're purchased. And thankfully, Ethereum has some mechanisms for this, so we don't have to read every pixel to find out what changed. The mechanism is Ethereum events. The idea with events is that our contracts can emit events at certain points in our code. These events can be indexed, which means we can find specific events very quickly. In our case, we're going to emit a pixel changed event whenever a pixel changes. Later on, when we build a UI, we will subscribe to these events using Web3 over WebSockets and automatically update each pixel as it changes. To specify an event in Solidity, we use the event keyword. We'll type event pixel changed, and it will have 3 arguments: the X position, the Y position, and the color. We emit an event by using parentheses like we're invoking a function. Here we can add this event to colorPixel. Now when we call colorPixel, Remix will also show us the logged event as well. There are 3 important things to know about events. The event can be indexed, the data cannot be accessed by the smart contract, and the data is available for as long as the block data is available. Event parameters can be indexed by using the indexed keyword. When you index an argument, you can search for those values, but know that you cannot retrieve the values themselves. In our case, we don't need any indexed arguments. Our event is already indexed to the contract and the event name, and we don't need to index it beyond that. Data emitted by events is not accessible to our smart contract. This data will live in the blockchain log. Its function is primarily for use by tooling outside of our contract, that is, in our ＤApps interface. Lastly, these logs are available for as long as the block data is available. The consequence here is that these logs are already on our machine alongside our blockchain. We can search for logs using filters such as the block number. That is, we can say, show me all events for pixel changed after block 3000. Events can be used as a convenient record of changes. They also can be used for optimizations for your UI. For example, in the million Ether page code, what we have is an XY grid of 1,000,000 pixels. In the naive case, if we wanted to draw the whole image, we had to make 1,000,000 calls, one for each pixel. However, with events, we can snapshot the image periodically and then query for the events that made changes after that point. But the general idea is that you can emit events in your code, and then your tooling and UI outside of the EVM can query and subscribe to those events. We'll do that when we build our UIs. There's one major constraint of EVM smart contracts that we've swept under the rug so far, and that is the issue of gas. So far, we've acted as if we have infinite Ether and unlimited computing resources available to us. But in reality, this isn't the case. When we write Solidity smart contracts, we're writing code that will be executed on someone else's computer. Actually, our code will be executed on thousands of computers. We have to ask, what happens if we wrote malicious code? For example, what if we wrote code that went into an infinite loop and submitted it to the network? If every node on the network were to fall into an infinite loop, the entire Ethereum network would halt. Could we analyze a program before we run it and check and see if it will terminate? As you probably already know, this is referred to as the halting problem, and the answer is no. The halting problem is undecidable over Turing complete languages. That is, the only way to tell if a program will finish is to actually run it. So what can we do? The EVM gives resource constraints on our programs. Essentially, it costs you money, or Ether, to run any program. If you make your program run for a long time, you'll pay a lot of Ether. The constraint on running our programs is called gas. That gas is a unit. Let me explain. Remember that the EVM runs bytecode operations, called opcodes, not our Solidity code. Each opcode costs a certain amount of gas to run. Some opcodes are cheap, like adding two numbers together, and some opcodes are very expensive, like storing data on the blockchain. But the gas cost for each opcode is essentially fixed. It's always going to cost 3 gas to add two numbers together. When we submit a transaction that calls a function on our smart contract, the total gas spent will be the sum total of the gas for each of our opcodes that was run. But we don't pay in gas, we pay in Ether. So how do we convert between the two? Well, the miners decide the price per gas that they'll accept. So for our example, if the price is 5 Wei per gas, and remember, a Wei is the smallest unit of Ether. So if the price is 5 Wei per gas, and we add two numbers together, which costs 3 gas, then we'll pay 5 times 3, 15 Wei for that operation. It can be a little confusing at first, so maybe an analogy will help. Say that I have a gas-guzzling camper, and I want to drive from LA to San Francisco. It's 374 miles, but let's round up to 400. My camper gets 10 miles to the gallon. It's 400 miles, so 400 divided by 10. I'll use 40 gallons of gas on my trip. But how much will I pay for those gallons? Well, it depends on the price of gas. So let's say the price is the same at every gas station along the way, and I pay $4 per gallon. So my cost will be $160 to make that trip. And let's say during my stay, there's a shortage and the gas prices have shot up to $6 a gallon. How much gas will I use on my way home? The same amount. It's the same distance back, and my car gets the same gas mileage, so we're going to use the same number of gallons of gas. How much gas I'm going to use doesn't change just because the price changes. It's the same way with the gas market in Ethereum. Your program will use the same amount of gas no matter what the price is because it has the same opcodes. What might change is how much that gas costs. So, there are two things we need to figure out. 1. How much gas does our contract call or transaction use? And 2, how much Ether will that gas cost? Let's look at each of these separately. Sol provides tools to estimate how much gas a particular method call or transaction will use. If you use Remix, it will provide those estimates in the UI. But it's important to remember that these are just estimates. Without running the code, you can't know precisely. And even if you run the code locally and measure how much gas was used, the state may change by the time you submit your real transaction, which could change the gas costs. Let's say that our transaction costs are 20,000 gas to run. How much are we going to end up paying in Ether? The easiest way to estimate gas costs is to find a website that publishes the current price. As I'm recording this, ethstats.net and ethgasstation.info both publish this information. However, if those sites don't work, check the comments for a new list of sites. But the idea is that if you find the gas price on that page, that price may not be denominated in Ether nor Wei. At the moment, I see that it's denominated in Gigawei, which is a billion Wei. To calculate the cost of our transaction, we multiply the gas used times that price per gas. We can do this in our Geth console like this. So our estimate is 20,000. That's the estimated gas used by our transaction. And our gas price is 25 Gigawei. And remember, the miners set this price. We can estimate the total cost in Wei by multiplying the gas price times the estimate. We'll use the Web3 two-way function to convert our gas price. Now, that's a large number and it's difficult to understand in this format, so let's convert it to Ether. There we go. And if you want to convert into your local fiat currency, you can just multiply this number times the cost of 1 ETH. Say, for example, that an ETH costs $75 US. Then we just multiply what we calculated before times ETH in USD. So if an ETH was $75 US, then the cost of this transaction would be just under 4 cents. Or if the cost of an ETH was $500, then the cost of this transaction would be the equivalent of 25 cents. So that's the basics of calculating gas costs. One thing you should also know is that blocks have a total gas limit. At the time I'm recording this, the limit is between 4 and 6 million, depending on the day. That is, the total gas used by all transactions in that block need to total less than 4 to 6 million gas. When we send transactions, we have to specify how much we're willing to spend on gas to run that transaction. And if you don't send along enough gas, your transaction will fail with an out of gas error. You should also know the gas that's spent is not returned to you. This makes sense from the miner's perspective. They still had to use their resources to process your transaction, so they'll keep the gas fees even though your transaction failed. A more advanced issue with gas comes up when we have our contracts calling other contracts. The idea is that we sometimes want our contracts to forward along some spare gas to a neighboring contract. But we'll talk about this when we get there. To recap, to calculate your gas costs, estimate the cost of your transaction by using tooling like Remix or Solk, or by running a test transaction locally. Find the market gas price, and then multiply the gas price times the gas you'll spend. It's time to build the UI for our DApp. We're going to build an HTML, CSS, JavaScript page, which will display the pixels that we have on the blockchain. Keep this in mind. What we're building is a visualization of the true data that exists on the blockchain. That is, our page isn't the source of truth, it's a visualization. This means that this app could run locally on anyone's computer without connecting to the broader internet, as long as they have our code and the Ethereum blockchain on their local machine. To build our boilerplate for this app, we're going to use NWB like we did in the earlier course. Again, in a real app, I'd probably use a web framework like Angular or React, but for now, vanilla JavaScript will be just fine. npm install-g nwb, and we already have a million ether page, so let's create our app in there. This time we use nwb init. Now install Web3, which gives us a connection to our Ethereum node, and get pixels, which we'll use to read the image files later on. All right, now we have our boilerplate, so let's draw on a canvas. To draw pixels on a page, we first need to understand how to draw pixels on a canvas. In this video, we're going to quickly cover the HTML Canvas API and show how we can use it to draw colors. The first thing we need to do is add a canvas tag to our HTML page. In our canvas tag, we specify a width and height in the number of pixels that we want to show. In this case, we'll do a width of 1,000 and height of 1,000 because that will give us 1,000,000 pixels. In source/index.js, the first thing we want to do is create a draw function, and we'll call this function when the body has loaded. Next, we need to fetch the canvas element from the page and start working with it. There are a few layers of APIs we need to go through to get to what we want. But what we're about to do is get the pixel data from the canvas and write new pixels onto it. The API can be a little involved at first, but I'll walk through each step, and you can check out the Canvas API documentation if you want to learn about the details. From our canvas, we get what's called a drawing context. In this case, we want a 2D context, which lets us draw pixels. Next, we read the image data from the drawing context by using getImageData. The arguments mean we want to start at the first pixel 0, 0 and capture the entire image up to canvas width, canvas height. This returns an image data object, and the image data object has a data field which actually stores our pixels. Here's the problem though. Our data field is a one-dimensional array. We don't access this object with an X and Y. Instead, each pixel is 4 positions, one for each red, green, blue alpha. So to access each pixel, we'll skip ahead by 4. Let's try it out. Here we iterate over all the data and increment by 4 on each loop. Each pixel will be at index I plus an offset for the channel. So red is +0, green is +1, blue is +2, and alpha is +3. Let's set each pixel to some color we can test. Here we need to set the color to a number between 0 and 255. So I'll just modulo I with 255. Now that we have new pixels in the data, we have to print it out to the screen. We do that by using context.putImageData. Let's check it out on our screen. When we try this out, you can see that we have these grayish lines. Let's try removing the green and blue channels. Now notice that we get red and pink lines. What's happening here is that as I is incremented, we're setting a stronger value for both the red channel and the alpha. What if we wanted to show random colors? We could create this function, which will pick a somewhat random number between 0 and 255, and then pass it to each channel. What we get here is noise. It looks gross, but it's what we were going for. Play around with this and see if you can make something prettier. Web3 can connect to our Ethereum node using WebSockets. WebSockets will let us keep a two-way connection open between our browser and our client. This means that our Geth node will be able to push real-time updates to our browser. We'll use this on our page to instantly draw any pixels that are purchased. In order to use WebSockets with Geth, we need to add some parameters to our Geth command. They look like the flags we used for RPC, only they begin with WS for WebSockets. Here's the command, which you can copy and paste from the video notes. Now in our index.js, let's connect to Geth using the Web3 WebSocket provider. We'll write a function checkBalance. Let's check our account balances just to make sure the connection works. And let's add this checkBalance function to our document on load. If we take a look in our browser console, we can see that the account balance is there, so it worked. If you didn't see those balances, double check that your Geth is running and that the hostname and port match. Now let's connect to the app in our browser and listen for events. I'm going to be using Remix for this video, but remember that you don't have to. You can use the Geth console or any other method you want to deploy your contracts. Right now I have RemixD and Geth running in my terminal. I also have my accounts unlocked and Geth set up to mine. We start by deploying our contract and then grab the contract address in the ABI. So from Remix, I'll copy the ABI, and save it to a file. And then we can import the ABI into our JavaScript and paste in the address. Then we can create an instance of this contract using web3.eth.contract and passing in the ABI and the address. We don't need the checkBalance function anymore, so let's get rid of it. Now that we have our contract instance, there are two methods we can use to read events. The first one gets historic events, and the second one subscribes to all new events. We haven't generated any events for this contract yet, so let's start with subscribing to new events. The contract instance exposes events on the events key. Here's how we can watch for all new pixel changed events. We'll type mep.events.pixelchanged, and we're searching from block 0, and then we'll log out any of the events. Let's send an event that changes the pixels. So I'll call setPixel74. I'll click this button to set a pixel, and quickly flip back over to our UI and watch the console. It works! We were pushed an event from our smart contract over WebSockets and into JavaScript. One particularly useful property of this event object is return values. Notice here that it has 3, the X, the Y, and the hex bytes representing our color code. This is the data that we'll use to draw on our page. To read past events, we'll use the getPastEvents function, and then pass the name of the event like this. We'll type mep.getPastEvents, and the name of the event, pixel changed, and here we'll say we want from block 3, and then log it out. Where I'm writing from block 3, that's an example of a filter. We can use filters to limit the scope of events we're interested in. In this case, we'd only get events that happen in block 3 and beyond. Let's try it by refreshing our page and checking the console. Nice! Notice that we have an array of events, which is all of the pixel-changed events that have happened since block 3. Now that we have these key components, we can start drawing a real image. We have pixel-changed events coming over WebSockets, and we need to draw them on our canvas. What we need to do is capture each event, parse the color string, and then write the pixel to the canvas. Let's take each step at a time. First, take a look at the event that comes through. The X, Y, and color are all strings, but we want them all to be integers. Actually, X and Y are plain integers, and we need to parse the color into 3 integers, RGB, each one being between 0 and 255. Let's write a function that, given an event, will parse these values and write the pixel. We'll name this function writePixel with event, and it takes an event as an argument. And then from that event, we'll extract the X, Y, and color from event.returnValues. Then we want to write the pixel. We haven't written write pixel yet, but we will. We'll type write pixel, we'll parse int X, parse int Y, and we need to parse the color. We'll write parse color too. Let's write parse color now. Parse color will take this raw color string, split the bytes, and convert it to a 3-element array, each element corresponding to a channel, red, green, or blue. You don't need to worry too much about how this function works, just know that it returns a 3-element array. Now we need to write this particular pixel to the canvas. What we're going to do is read the current image data, find the index for this pixel, and update its color. Let's write the write pixel function. It takes 3 arguments, the X position, the Y position, and the color, and let's log those out. First, we'll grab the existing image data, and then we'll grab the width and the height from the canvas. And notice that the canvas is in scope here. Now finding the index is a little tricky because the image data is a one-dimensional array. How do we find the index in a one-dimensional array? First we'll take the Y value times the number of columns plus the X value times 4. Why 4? Because we have 1 byte per channel per pixel. If that seems confusing, try to work it out on paper, but honestly, understanding the layout of this image array in memory is not that crucial to building this app. This is how you find the index. Now we will assign the pixel in data each channel of our pixel in color. The first one being red, then green, then blue. And I want every pixel to be opaque, that is, no transparency. So I'll set the alpha channel to 255. If you don't do this, your pixels will be invisible. And lastly, we put the image data back onto the canvas. You might read this and realize that we're rewriting the canvas on every new pixel. You could certainly batch these updates, but we're not going to for this video. Now, all we have to do is change our event subscriptions to send the events to write pixel with event. All right, we don't need this anymore. And whenever a new pixel changes, we'll write pixel with event there. Here we'll type events.map and then pass that to write pixel with event. If your page reloads and all you see is a white screen, look closer. A pixel's a pixel, no matter how small. And if you zoom real close, you'll see pink on the wall. But if we add more pixels, it's easy, you see. We just type 340x0c. We have 2 pixels rendering. Let's refresh the page, and they should still reappear because we're using the same function to load old events as reading in new events. But these pixels are too tiny to see. So here's an idea. Let's buy an entire image. We want to be able to see way more pixels on our page. No one wants to sit and buy each individual pixel by hand. Instead, what we're going to do is write a script that will take an image and a location as input, and then submit the necessary transactions to Geth to color these pixels. Before we can do that though, we need to write a script that will read an image. We're going to use the getPixels library to read these images. First, let's create a scripts folder to save this utility script. The first thing we'll do is require getPixels. Next, we process the command line arguments. For a real command line tool, I'd probably use a library like yargs, but we'll just use process.argv for now. The arguments will be the image path, the X position, and the Y position. We're going to be using the des to hex version that we wrote in an earlier video. We call getPixels with the image path, and it calls back with the pixels from that image. Next, from the image, we'll extract the frames, the width, the height, and the channels. I found this API by reading the getPixels documentation. The frames parameter is used for when you're loading an animated GIF, but we're only going to use the first frame. Next, let's log out some basic info about this image. The next thing we need to do is iterate over each pixel. We'll iterate over every pixel in the width, every pixel in the height, and we get the individual channels from pixels using pixels.get and passing the frame, the X and the Y, and then the index of the channel. So for example, the red pixel comes from frame 0 at our XY position, and it's the 0th index. Pixels.get returns a number from 0 to 255. But remember, when we send this transaction to Ethereum, we need to send a hexadecimal number. So we'll convert back using the des to hex function we talked about earlier. For now, let's just log this out. And let's try it out. I've grabbed this GIF from the internet. There we go. Now we have the index of each pixel along with a hex color code. From here, we can form these pixels into Ethereum transactions. Now that we have a script that can read an image, let's color each pixel on the blockchain. What we're going to do is iterate over each pixel and send a transaction for each pixel we want to color. Of course, this can be a lot of transactions, especially if the image is large. But the idea is that someone is purchasing a scarce pixel for a long period of time, so it's not that big of a deal if it takes a while to buy the whole image. The first thing we need to do is connect to our Web3 node. Type const web3 equals require web3, and then create a new instance. We'll set the provider to the HTTP provider at localhost 8545. Here, I'm using the HTTP provider, but it's worth looking into the IPC provider too. Next, we need to get a handle on our contract. We'll do this, like we have before, by loading the ABI and looking up the contract's deployed address. Because we're sending transactions, we'll also need the sending account address. Normally you'd configure this as an environment variable or command line argument, but we can hard code it for now. Now with this contract, when we loop over each pixel, instead of logging it, we want to call the color pixel method on the contract to send the transaction. We do that by writing mep.methods.colorPixel, then we pass the X position, the Y position, and then the pixel as a hexadecimal string. And then we send from our account. Remember that each pixel can be placed in a particular position on the board. So as we write each pixel, we add the XPOS and the YPOS as an offset. We can control the location of the image this way. To try this out, make sure that you have Geth running and you've unlocked your account, the same account that you coded above. Also, make sure that you have a miner running. One thing to note is that this can send a lot of transactions, and so you need to make sure that you have enough miners running. Here, I'm going to start 3 miner threads in Geth. Now we can try it out and watch in our browser as the pixels load. Nice. For small images, this probably works for you. But if you try it with larger images, you'll notice that you have missing pixels. The reason is each node limits the number of unmined transactions allowed from a sending address. Instead, we should issue our transaction in chunks and then wait for them to be mined. To do this, we can wrap our pixel writing code in an async function. What we'll do is submit a group of transactions and then wait for them to be mined before we submit the next group. This will allow our network time to catch up. Each time we send a transaction, the return value is a promise, and this promise is fulfilled when the transaction is mined. We can store that promise in a list of promises. We don't need to wait for every single transaction. Instead, we can just wait for, say, every 128 or every 64 transactions. So if I mod 128 is equal to 0, we'll pause and wait for at least one transaction to be mined. Here, we're using promise.race, which will continue as soon as the first promise in the group is resolved. If you wanted more reliability, you could use promise.all instead. At the end, we'll call sendPixels and then wait for it to finish. Now let's try this out with a bigger image. This might take a little while to run. There we go. We can color pixels using an image, but we still have the problem that these pixels are open for anyone to write over for free. So let's modify our contract so that you have to send funds and bid for each pixel in order to control it. Our goal here is to improve this smart contract so that people can bid on a pixel with Ether. These next few videos really get at the heart of smart contracts because we're going to be writing a contract that can hold its own funds and releases them according to our code. The behavior we want is to require that color pixel be sent Ether in order to allow coloration. We want to require that the amount sent is higher than the previous amount paid for that pixel. If you try to buy a pixel at too low of a bid, your funds should be returned to you. If you are the highest bid, then your funds are stored in the contract. If you're outbid by someone else, your funds should be returned to you and you can try again. Right now, our pixels array holds 1,000,000 bytes 3. But if each pixel can have an owner and a sold price, we need to keep track of that extra information. The way we do that is by using a Solidity struct. Instead of a pixel being merely a bytes 3, we'll create a struct called pixel, which stores the address of the owner, the sold price, and the color. In this case, our pixels property becomes a 2D array of pixel structs. When we want to write a new pixel, we'll send ether along with the transaction to the contract. And if the ether value is greater than the last sold price of that pixel, then we'll update the pixel color, owner, and new sold price. While the final code won't be that long, there are several new ideas here that require some care. Let's tackle them one at a time, starting with payable contracts. All right, a contract can own funds. Remember how in the Geth console we check the balance of our accounts? What's happening here? That hash is the address of our account, and the Ethereum blockchain stores the number of ether assigned to that account. We can do the exact same thing with contracts. Remember how our contract is deployed at a particular address? That address is also the contract's account address, and that account can hold a balance controlled by the contract. To explore this idea, let's create a simple bank contract. In this bank, we can deposit funds. When funds are deposited, we'll create a new event called deposit made, which has the address that the deposit was sent by and the amount. Our deposit function has a new modifier called payable. Payable functions are functions that can accept ether value when called. That is, when we send the transaction, we send not only the function arguments, but also an additional amount of ether from our account to the contract's account. And we can use that value in our function. When we call contract functions, there are a number of global or context variables that we can access. This is the first time we've talked about these, and there are two that we're going to use: message.sender and message.value. Message.sender is the address of the incoming transaction. So if we call this message from our account, message.sender would be our account address. Message.value is the amount of ether that was sent with the call to this function from the incoming transaction. You can think of these as invisible arguments. Let's deploy this contract and try it. When a deposit is made with this function, we'll emit the deposit made event and pass the message sender and the message value as the arguments. If we hit the deposit button, you'll see a new event is created, but the value that was sent was 0. To send a value in Remix, we'll just add on to this value field, and you can do the same thing in Geth. Let's add 3 ether. Now let's copy the address of this contract and check the balance in our Geth console. We have value. The contract now has a balance of ether of its own. The contract owns these ether, not us. And let's say we want our money back. Well, we can't get it. We didn't code any way to get the funds out of this contract. Oops. But there is one common way to get ether out of a contract, and that is to set it up to give us the funds back when the contract self-destructs. The ether in this contract is lost, so let's improve this code and deploy a new one. Common pattern in Solidity contracts is specifying an owner. The idea is this: when we create a contract, in the contract's constructor, we'll store the address of the account that created this contract. That account becomes the owner. And in our code, we can grant special privileges to the owner by checking that the message sender is the person who created the contract. In this case, when the contract is destroyed, we'll send the funds back to that owner. Here's how we modify our bank contract to have an owner. First, we'll add an address property to store the owner. And then we'll add a constructor function. Here we'll set the owner to the message.sender, that is, the address of the account that created this contract. Last, we'll add a destroy function. And this function will call self-destruct, which is a special function that essentially shuts down our contract. The argument to self-destruct is the address where we want to send all of the funds that this contract controls. Notice here that the owner property is not a magic variable in Solidity. That is, it's a normal address that we're keeping in storage, like any other variable we keep in storage. It's only the logic that we have in our code that gives it special privileges. One problem with our destroy function is that anyone can call that function. We don't have any constraints on who can call destroy and self-destruct our contract. Let's introduce one more Solidity concept, require. We only want the owner of the contract to be able to call destroy. If someone else calls destroy, we don't want self-destruct to be called. Do you remember how we check who is calling a function? We use message.sender. So we could have a simple if statement that checks that the message.sender is the owner. This would work, and if someone other than the owner tried to call destroy, it would fail silently. But Solidity has a mechanism that's sort of like raising an exception. It's called the require operator. We can add the require like this. Require message.sender = owner. Require checks the condition, and if the condition is false, it will revert all state changes up to that point. We use require for input validation, and we will be using require a lot. So let's try out self-destruct. First, we'll create the contract, and I'm going to select my second account here because the first account is where my mining rewards go. And you can see here that the owner address is our account address. Then we'll deposit 3 Ether to the bank. Now let's check our contract's balance. Looks good. And our account balance. Now let's destroy our contract. But first, let's try it from our first account. That is, the account that isn't the owner. It says, callback contains no result. Gas required exceeds limit. That error message isn't exactly clear, but what's happening here is that it did not accept our destroy transaction, which is what we want. Let's try it from the owner account. Great, it looks like it worked. Let's check our balances again. Good, our account has 3 more Ether, and our contract has a balance of 0. Now we know the basics of payable contracts, ownership, and using require. Let's use this to color pixels. To color a pixel, we're going to require that Ether is sent to buy the pixel. We have our pixel struct already, and we also want our pixel changed event to emit the new owner and sold price, along with the X, Y, and color as before. This way our UI can keep track of how much each pixel costs. Here's how we change color pixel. First, our color pixel function needs to be marked payable. We want to read the current pixel from our contract storage. Here we declare the type pixel, and we designate this variable as coming from storage. This is important because variables in storage cost a different amount of gas than variables in memory, and we don't want to copy data unnecessarily. This syntax means that our pixel object will reference the same pixel in storage, so any changes to this struct will be written to storage as well. We want to require that the message.value, that is, the amount of Ether sent along, is greater than the last sale price for this pixel. Pixels that haven't been set will have all values initialized to 0. So in the case of an unclaimed pixel, you just need to send a positive amount of Ether. If not enough Ether was sent to win the bid, then require will revert all state changes and exit from this function. The next line will only be run if the bid is highest. So we update the pixel's owner to the message.sender. We set the sold price to be the current value of this transaction, and then we set the new color. Lastly, we'll emit the event that says all of this happened. Let's try it out. First, we'll create the contract. Next, we'll try to create a pixel without sending any value. It didn't work. That's because the require statement triggered. So let's add some value. It looks like it worked. Let's grab that pixel. Nice. Notice that it shows not only the color, but also our address as the owner and the price that it sold for. Let's try to buy that same pixel at a lower price. Again, it doesn't work, but if we increase our bid, it does. Now, there's one problem with our setup. The contract keeps all the money, and we have no way to get it out. What we want to do is this. If someone is outbid, they should receive a refund for their previous bid. Let's add that. Now we're trying something new. We want a contract to send funds to another address. And before we get started, I want to point out we're entering a danger zone. What's the worst thing that can happen to your smart contracts? The worst thing is for it to have a bug that causes people to lose money in unintended ways. Because sending funds is such a major part of smart contracts, Solidity and Ethereum have a number of ways to send value around. The problem is, this flexibility means that bugs can be introduced in subtle ways. Since this is the first time we've talked about contracts sending funds, I want to focus on the high-level ideas, but do not release code in production that handles real funds until we've had time to talk through the other security pitfalls. For example, we haven't talked about reentrancy yet, nor have we discussed fallback functions or contracts calling other contracts. We will, but I want to make the point that this video teaches you enough Solidity to be dangerous, and we need to talk more about the implication of contracts sending funds before you release a production app. Okay, with that out of the way, let's get back to our bank example. In this contract, we accepted deposits, but we didn't keep track of them. The only way to get the money back out of the bank was to destroy the contract and send the money back to the contract owner. Let's fix this. We'll start by adding a new property to the bank called balances, which will be a mapping that keeps track of how much Ether was sent by which address. Think of it as keeping track of different bank accounts. Say mapping from an address to a uint, and it's public to list the balances. This property has a key, which is a particular address, and a value, which is the amount of funds designated for that address. When someone makes a deposit, we want to credit their account balance. So let's add this line to the deposit function. Balances for that sender increment by the message value. And note that because this is an unsigned integer, we should be checking for overflows, but we'll talk about safe math later. This will add the message.value amount to the current balance for this address. Keep in mind that this balances property is internal logic for keeping track of the balance for each address. That is, the contract itself has one account balance, that is, the true Ethereum network recognized total balance owned by this contract. This logic, keeping track of account balances, is totally internal bookkeeping. We could set these balances to whatever we want, and it doesn't directly affect the true amount of Ether that the contract controls. The contract holds a total amount of real Ether, and this balances mapping is just for our contract's internal bookkeeping. Try putting this script into Remix and play around with the deposit function and confirm for yourself that it works. To write our withdraw function, how do we actually send funds from our contract to another address? There are several Solidity constructs for sending funds. They have differing semantics, and we need to be very careful about which we choose. The two that we'll talk about right now are .send and .transfer. We use .send like this. Given an address, we call .send on that address, and we send an amount. If .send fails, it will return false, not revert changes. This means we need to check the return value of .send every time we use it. So every time you use .send, it should look like this. If the negation of calling some address .send is true, then handle the failure by reverting the necessary changes. .transfer is a high-level version of .send that will revert changes if .send fails. That is, .transfer is equivalent to if send fails, revert changes. This is similar to throwing an exception. And remember that if .transfer fails, all state changes will be reverted and the function will exit. But there's a question. Why would sending funds to another address fail? If you send funds to a normal address, it won't fail. It will just accept your funds. But in Ethereum, your contract can send funds to another contract. And when you send funds to a contract, that contract can run logic too. And you don't always know whether it's going to a normal account or to a contract account. Sometimes the contract receiving your funds will run logic that fails, and you need to be prepared for that. Ignoring it can lead to really subtle bugs. In fact, sometimes the contract receiving your funds is malicious and designed to deliberately fail. We'll talk through an attack scenario like this in the future bank robber video. But for now, know that when you send funds, it might fail and you need to deal with that. Now, let's withdraw these funds. Let's start with 2 rules. 1. You have to withdraw all of your funds. That is, there's no partial withdrawals right now. And 2, an address can only withdraw their own funds. Here is a buggy and wrong way to do this. So to the message sender, we'll send the value that's in balances of the message sender, and then we'll set their balances to 0. What's wrong with this code? Well, the problem is that we're sending the funds and then clearing the balance without checking to see if the send succeeded. One failure scenario here is that the send fails because the receiving contract runs out of gas. Then we set their balance to 0, but the Ether wasn't transferred. In this case, we'd unfairly clear their balance, but keep their Ether in the bank. A worse scenario is possible, where all of the funds in the contract could be drained by an attacker because of a feature called reentrancy. I'll walk through an example of that in the bank robber video too. Instead, what we should do is clear the balance, send the value, and then check to make sure the send succeeded. If it failed, we need to restore their old balance. Let me show you 3 ways we could do this. First, we're going to pull the current balance into the variable balance. Next, we'll set the balance of this account to 0 before sending any funds. This ensures that if the withdraw function is called again before we're done, the sender won't have any funds left over. Next, we'll use .send to send the balance and check the return value. If the return value is false, then we'll call the code in that block. Here, we're manually resetting the balance back to what it was. This is a somewhat manual way of handling the error. You would use this case when you want a little more control over how to handle the failure case. The second way we might write this starts out like the first. Only in this case, if .send fails, we're calling revert. Revert will revert all of the state changes that happened during this call. This is different from the previous case in that the previous case handled the error by manually resetting the balance. But in this case, when we use revert, if our function was larger and had made other state changes, revert would undo all of those as well. Revert is a great idea to use when you want to say, this whole thing needs to fail. Revert all the changes so far. And the third way is syntactic sugar over the second way. Here we'll use .transfer, which, if you recall, is effectively the same thing as calling .send and revert if it failed. The main point is, be careful when you send funds. Check to make sure they succeed, and have a plan to deal with when sending the payment fails. Let's get back to the Million Ether page contract. Now that we have a grasp on how to send payments, let's issue refunds when a pixel is outbid. Taking a look at our color pixel function, the obvious solution would be, after we've verified that the new bid price is higher than the sold price, we should .send the funds back to the previous owner. That code might look like this. So we check that the message value is greater than the pixel sold price, and then we call pixel.owner.transfer pixel.soldPrice. That looks pretty clean. But wait a second. What do you think about this code? Are there any problems or potential attacks? Remember that .transfer will revert all changes if sending the funds fail. So if an attacker could craft a contract which buys the pixel and then always deliberately fails when you try to send it value, the result would be that no one could ever buy that pixel again. Every time someone outbids them, this contract would try to transfer the funds. But the transfer would fail, which means the contract would fail to instate the new bid and recolor the pixel. This sort of situation also comes up whenever you're looping over sending payments. For example, if you have a for loop where you need to send payments to several different contracts, make sure one contract failing won't prevent the addresses later in the loop from receiving their funds. This problem shows up in Ethereum smart contracts all the time, so much so that the solution has a name called the poll payment pattern. The idea applied here means that instead of sending the Ether refund in line, that is when a new pixel is purchased, we keep track of pending refunds internally. Then the account that receives the refund must submit a separate transaction to pull the funds out. Let's implement this pattern in our contract. We'll start by adding a pending refunds property, which is a mapping from an address to an amount. This is a lot like the list of accounts we had in our bank contract in the earlier video. It's a mapping from an address to a uint. It's public, and we'll call it pending refunds. When we color a pixel, instead of sending the Ether directly, we'll credit the pixel owner's account with a refund. First, we check that the pixel owner is not an empty address. And then we add on to pending refunds the old pixel owner's original price. Again, remember this doesn't transfer any Ether out of the contract. This is just internal bookkeeping. And also note again that any sort of math like this should be checking for overflows, but we'll talk about that later. And lastly, we'll write the withdraw refund function. And also, I want to mention that this function is based off of the OpenZeppelin pull payment library. You can find the URL in the notes. So the function withdraw refunds first takes the payee as the message.sender, and we look up the payment in pending refunds. We require that the payment not be 0, and we also require this.balance be greater than the amount of the payment. This.balance is the amount of Ether that belongs to this contract. Next, we zero out the pending refunds for this payee. Then we send the payee the payment and require that it succeeded. If it fails, we revert all of our state changes so far. Let's try it out. First, we can deploy this contract. Now let's buy a pixel for 1 Ether. Now let's try buying that pixel for fewer Ether from the other account. Notice that it doesn't run, and it returns quickly too. And that's because Remix will try to run the transaction locally before sending a real transaction to the network. Now, let's check the pending refund for our original account. Great, we can see our refund here. Now let's try to withdraw our refund. It worked. Notice the balance of Ether in our account went up. Let's check our refund balance now. It's 0, great. In the last video, we built a simple counter contract in Solidity. We deployed it to the blockchain and called methods on it to update the state. There's a lot more we have to learn about Solidity and smart contract programming, but I want to show how to make a connection all the way to our web browser. That is, I want to make a user interface for this contract. I think it's helpful to see how an Ethereum-based app is done end-to-end, and then we'll go back and learn how to make more sophisticated apps. To build a UI for our Ethereum app, the key idea is this. Our Ethereum node has a JSON API, and we'll connect our browser to that API. So the core architecture is that we have an HTML file, which loads JavaScript. And this JavaScript, instead of calling out to, say, a normal centralized server, will call to our personally controlled Ethereum node instead. Now, just to be clear, our web app is all just JavaScript. So you can call out to other servers if you want to, just like you can call lots of APIs in a normal JavaScript app. In fact, this really is just a normal JavaScript app. The only difference is that we're connecting to an Ethereum node for the API. The library that we use to connect our JavaScript code to the Ethereum JSON API is called Web3. To build our UI, we need to start with a basic HTML, CSS, JavaScript boilerplate. I'm not going to teach web development here. We have other books and courses if you want to learn that. Instead, I'm going to assume that you know how to write JavaScript, install NPM modules, and use promises. In a real app, I'd probably use a web framework like Angular or React, but I want to focus on what's new here, and so vanilla JavaScript will be fine. I also want to warn you that in this tutorial, we're going to take some JavaScript shortcuts, like creating global variables on window and directly manipulating the DOM. We'll cover how to properly structure larger Web3 apps later, but for now, let's just get it working. Everyone has their own favorite boilerplate, and I'm going to use NWB here, because it's an easy way to get a nice vanilla JavaScript app up and running. So we can install it first by doing npm install -g nwb. nwb new web app hello counter. Then I'll cd into hello counter, do an npm install. And then I'm going to npm install web3. We can start our server using npm start and then open localhost 3000 in our browser. A great thing about this configuration is that it will automatically reload our app whenever we change these files. We can open up the code and see that the basic app we're given has an index.html and an index.js. The first thing we'll do is require Web3. And the way the Web3 API works is we're going to call new on this object. So we'll declare a lowercase web3 equals new web3. And so we can expose variables to our console by setting them on window. So let's make web3 accessible to our browser console by typing window.web3 equals web3. The next thing to do is to set the web3 provider. In this case, we're just going to use the HTTP provider, but you could also use WebSockets if you wanted to get real-time updates. And notice that we're setting the address to localhost port 8545. This address is the address of our Geth RPC server. We haven't booted Geth in an RPC mode yet, so let's do that now. Flip back over to our Geth shell, kill it using Control-C, and let's start it with new options. So I'll use bin geth datadir. I'm going to set the options nodiscover, RPC, RPC API, and then a list of RPC APIs that we want to use. DB, personal, ETH, net, web3. There's several. These are the ones we'll use for now. And then there's a few other options. RPC cores domain, you don't need to worry about that for now. RPC address, I'll put localhost, RPC port 8545, and console. You can find this full command in the lesson notes. Feel free to adjust the RPC address or RPC port if you need to. For example, you might try using 0.0.0.0 for the RPC address if localhost doesn't work on your machine. You might also need to change the RPC port. But essentially what this will do is launch Geth in console in our shell, but it's also opening up an RPC server in the background, which our web browser can connect to. Now we should be connected to our Geth node. We can try it out by typing web3, web3.eth, web3.eth.personal, and web3.eth.personal get accounts. Now notice here when we call the get accounts function, it returns a promise. So if we want to actually get the result of our accounts, we'll type web3.eth.personal.getAccounts, and we'll call .then, and then we'll log out the results of that promise. If this didn't work for you, check out the network pane in your browser. But at this point, we should have Web3 connecting from our browser to our Geth RPC server node. Now what we want to do is write a button on our page that will allow us to check the balances of our accounts. We'll do that by writing app.innerHTML equals, and then we'll put an h2 tag to show some text, and then a button where on click we're going to call the check balance function. Now let's write a function that will check our account balances. Again, it's not a good practice to put functions on window, but we're just testing Web3 here. So we'll type window.checkbalance equals function, and first we'll call web3.eth.personal.getAccounts.then. We'll log out those accounts, and then we'll get the balance of the first address by typing web3.eth.getBalance account 0. That also returns a promise, so we'll call .then and log out the balance. Let's flip back over to our browser, try it out. Great, there you can see that we checked the balances of our Ethereum accounts in our browser.